So today we're going to solve problems using the thin lens equation. And the equation is 1 over f, which is the focal length, equals 1 over distance of the image plus 1 over distance of the object. So we're going to erase that. I'm going to put it in the top. So it's 1 over f equals 1 over distance of the image plus 1 over distance of the object. And also, for thin lenses, we're going to use magnification, which is m, equals negative distance of the image over distance of the object, or negative hi, which is height of the image, over ho, which is height of the object. So we're looking at, for a biconcave thin lens has a focal length of 10.0 centimeters. So we've got focal length equals 10.0 centimeters. Locate the image and find the magnification of an object at a distance of 25.0 centimeters in front of the lens. So we know that the distance of the object equals 25.0 centimeters. And we're trying to find the distance of the image, which is unknown, and we know it's going to be in centimeters, and the magnification, which is going to be just, there's no unit for magnification. So first we're going to have to draw our lens. So we have a straight edge. And a biconcave lens is drawn like an hourglass, or not really, yeah, kind of like an hourglass shape. So it goes like this, and then it's going to go, we're going to have a dotted line straight through it. And then you're going to have the focal length, which is over here, and that's going to be 10 centimeters. And then you're going to have the object over here, which is 25 centimeters. And then you have 2f, which is, let's see, it should be an equal distance. So it's going to be, over here. And that's going to be our 2f. Oh, wait, let me fix that. Okay, so that's 10 centimeters. This is going to be our 2f. So, for biconcave lenses, we have a parallel ray, a focal ray, and a central ray also, exactly like mirrors, except when it hits, so we have the object over here. So when it hits, it's going to reflect or diffuse or go through, depending on which one we're drawing. So now we're going to draw the parallel ray, and the parallel ray is basically, it's going to be a straight line to the lens, to the middle of the lens, and then it's going to go like this. So we have it, and it's going to go up like that. And then, so that's our parallel ray. Oh, wait, my bad. Oh, no, it's supposed to, actually, you have to draw it, the whole thing is supposed to go like this. So it's gonna go that looks a lot better. So it's going to look like that. Oh, sorry, smudged right there. And then you're going to have a focal ray, which is going to be a little different, and it's going to go to 2f it's going to go to 2f, and that's not very even, and then it's going to come out this way, so it's going to come out parallel to the parallel, right? And I completely messed that up. Sorry about that. So that's going to be our focal ray. And yeah, and then you have your point of intersection, but you can also have a, you don't need one, but it would help to have a central ray, just so you make sure that you have the right intersecting point. So you have, it's going to go through the center of the lens, or the bottom where the lens meets. So you're going to go, it's going to go like that. So we can now tell, this is going to be central, that the image is going to end up right here, and it's going to be upright. And now we can apply the formula to find out the distance of this image and its magnification. So we have 1 over the focal length, which is going to be 10, actually it's going to be negative 10 centimeters, because it's on this side. So everything on this side is going to be not going to be negative, but the focal length is going to be negative because we have the 2f over here, equals 1 over 25 centimeters plus 1 over di, which is the distance of the image, which we're not sure about yet. So you move this over here, so it's 1 over negative 10 centimeters minus 1 over 25 centimeters equals 1 over the distance of the image. And if we use our calculator, we can figure out that that equals negative point, no, not negative point, my bad, it's negative 7.142,857,143 centimeters. Or we can just reduce that and give it 1 decimal point, so it's going to be 7.1 centimeters. And that does look accurate because we have the focal length, which is right here, and it's between the focal length and the lens, so 7 centimeters seems about right. And then now we're going to erase that work. And we're going to do the magnification. So we're going to remember that the distance of the image is negative 7.1. So we have the magnification equals negative 7.1. Always remember this negative right here, or else your whole equation will be messed up. And then you have it over the distance of the object, which is going to be 25. So your magnification is going to equal 0.29, and it is positive, which means that the image is upright, and the image is virtual because it's on the same side as the object. So we have virtual, the image is upright, and it is smaller than the actual object, and we can just tell that, we can estimate that by the image. And since we don't have the height of the object, we cannot find the height of the image, but that's how you figure out the distance of the image and its magnification for a biconcave thin lens.